Welcome back to Science Click. Today, temperature and heat. Let's take an object, for instance, an apple. This apple looks perfectly still. However, if we look at the microscopic scale, the apple is actually made up of a multitude of molecules, which are themselves made up of atoms. These molecules, of which the apple is composed, are constantly in motion. They move very quickly and keep colliding with each other. Thus, even though from the outside the apple appears perfectly still, inside it, all the molecules that compose it are actually in constant movement. It is this degree of microscopic agitation at the level of the molecules of an object which we call its temperature. If the molecules in the apple were more agitated, we would say that the apple's temperature is higher. Inversely, if the molecules were less agitated, we would say that the apple's temperature is lower. In the universe, there is a whole range of different temperatures. Some objects are very hot with very high temperatures, while some are very cold with very low temperatures. However, it would be impossible to find anything colder than -273.15 degrees Celsius. Indeed, at this extremely low temperature, the object's molecules would be so still that they would in fact be completely motionless. It is therefore impossible to cool down an object any further, as it would have already lost all its agitation. This minimum temperature is called absolute zero. In practice, it is impossible to reach absolute zero. However, we can, in laboratories, approach it to within a few tenths of a billionth of a degree. All objects in our universe have a certain temperature. However, the temperature of an object can change over time, and this generally occurs through the exchange of a certain type of energy which we call heat. For example, an object A can transfer heat to an object B. On one side, A will cool down because it loses energy, and on the other side, B will warm up because it absorbs the energy which has been transmitted. There are three types of processes in the universe that allow objects to exchange heat. First, if a warm object is brought into contact with a colder one, the molecules of the warmer object, which are very agitated, will collide with the molecules of the cold object and thus transfer over some of their agitation. This is called thermal conduction. In this way, when we touch a cold object, our body communicates a part of its energy to this object, and thus, having lost some heat, we feel a sensation of cold in our hand. Thermal energy can also be carried by the movement of a liquid or a gas. For example, if we heat a glass of water from the bottom, the water at the bottom will be hotter than the water at the top. Since cold water is more dense, it will sink to the bottom of the glass, while the hot water will rise. The agitation, which was first localized at the bottom, has therefore spread in the glass with the water motion. This is called convection. Finally, all objects convert a part of their internal agitation into electromagnetic energy, that is, radiation. The hotter the object, the more energetic the radiation. For example, our human body, which is not very hot, emits infrared light, which is not visible to the naked eye but can be detected by thermal cameras. The sun, on the other hand, has an extremely high temperature. It is therefore constantly emitting radiation, infrared, visible light, ultraviolet, which propagates through the vacuum of space. Some of this radiation reaches Earth, and by absorbing a part of it, the Earth's surface gains heat and consequently warms up. This phenomenon, which turns agitation into radiation and vice versa, is the only process that enables heat to be exchanged through a vacuum. It is thanks to this phenomenon that the Sun is able to warm up the Earth from tens of millions of kilometers away. This is what has allowed the presence of liquid water on our planet's surface and the development of complex life as we know it.